Okay, let's unpack this. I want you to picture a challenge. I am handing you a massive stack of digital files, raw, messy, human data.
Right.
We are talking about thousands and thousands of records from the mid-90s. We have ages, education levels, marital statuses, job titles, home countries, all of it, and your only mission is to look at all that chaos and predict, with some kind of mathematical certainty, whether a specific person earns more or less than $50,000 a year.
It sounds like a game show premise, doesn't it?
Yeah.
But you've just perfectly described one of the absolute classic benchmark problems in machine learning.
Yeah.
This is, in many ways, the hello world of classification algorithms.
Exactly. And today, we're not just skimming the surface. We've had some feedback that you guys want the nitty-gritty. You want to know how the gears actually turn inside these models.
The nuts and bolts.
The nuts and bolts. So if you're driving right now or you're at the gym, this is for you. Lock in. We are diving deep into a technical paper titled Supervised Learning for Binary Classification on U.S. Adult Income by Liepeng Chen. We're stripping the engine down to its components.
We really are. We're taking data from the 1994 U.S. Census, which, it acts as this fascinating, slightly pixelated snapshot of American society from that era, and we're using it as a battleground, a proving ground for 6 very distinct algorithms.
And these aren't all the same, are they? We've got a real mix.
A huge mix. We've got the old guard, the classical statistical methods going toe-to-toe with the real heavy hitters of modern machine learning. It's a proper showdown.
And I want to be really clear about the mission here for everyone listening. We aren't just going to tell you algorithm it won, that's boring, that's a headline.
Right.
We want to understand why it won. Why does one model see the pattern and another one just, I don't know, crash and burn? What is the math actually doing in the background?
Precisely. We are going to map out a journey comparing these 6 different approaches. We'll start with the linear basics, your logistic regression, your discriminant analysis.
The ones you learn in Stats 101.
Pretty much. And then we'll move into the more black box territory. We're talking support vector machines, we're talking random forests, and the ultimate contender in this paper, boosting. The whole goal is to see which mathematical philosophy best handles the absolute noise and entropy of real human lives.
And the target, the thing we're trying to predict, is simple, right? It's a straight-up binary choice.
It's binary classification in its purest form. We're defining a target variable, let's call it $, and dollars can only be one of 2 states. Yes, the person's income is greater than $50,000, or no, it's less than or equal to $50,000.
It's a zero-sum game. You predict right or you predict wrong. There's no in-between.
That's it.
Okay, so before we let these algorithms loose, we have to talk about the raw material, the fuel for the engine, the data set itself. What are we actually looking at here? What's in the box?
So this is the famous adult data set. It's hosted at the UCI Machine Learning Repository. It's a classic. It contains 48,842 individual records.
That's a lot of people.
It's a very substantial sample size, especially when you think about the computational power that was available when this data was first aggregated and studied. And for each of those people, we're looking at 14 distinct attributes or, features.
And these aren't just abstract numbers. These are descriptors of people's lives. We have things like age, work class, which is, what are you, from the private sector, government, self-employed?
Exactly. Then you've got education level, marital status, race, gender, capital gains, capital losses, hours worked per week. It's a real slice of life.
It really is.
But, from a data science perspective, the very first thing that jumps out at you isn't the sociology of it all. It's the imbalance. This is a critical challenge right out of the gate.
An imbalance. What do you mean by that? In what way?
The target variable, that $, we talked about, it's not split 50-50. It's not an even coin toss. The data actually shows that 76.07% of the people in this data set earn $50,000 or less.
76%.
76. And only 23.93% are in that high income bracket we're trying to find.
Wait, hold on a second. Pause there for a second. You're telling me that more than 3/4 of the people in this data set make less than $50,000 a year.
That is correct, in this 1994 sample.
So, let me get this straight. If I just wrote a really dumb script, no AI, no machine learning, just a single line of code that printed no for every single person, just guessed low income every time,
Yep.
I would have 76% accuracy.
You absolutely would. And that has a name. That's what we call the no information rate.
Yeah.
That's your baseline. Any model we build has to beat that or it's useless.
Then why are we here? I mean, seriously, if these fancy algorithms you're about to show me, these random forests, these SVMs, all this complex math and compute power, if they come back and say, hey, we got 78% accuracy, aren't they basically failures?
They are.
We're doing a massive amount of computation for a measly 2% gain over a dumb guess.
What? That is the exact skepticism you should have.
Yeah.
And spoiler alert, some of the models we're going to discuss today do barely beat that dumb guess. But the goal here isn't just raw accuracy. It's about discrimination. It's about finding the signal in the noise.
Okay.
If you guess no for everyone, you have 0% accuracy on the high-income people. You miss every single opportunity to identify a high earner. You're basically saying they don't exist. We're trying to find the needle on the haystack, not just describe the size of the hay.
Okay, that's a fair point. We aren't just trying to be right on average. We are specifically trying to find that 24%. But the deck is stacked against us from the start. And it gets worse, doesn't it? Because real-world data is never clean. It's always dirty data.
It's always dirty. In this data set, the researchers found that a pretty significant chunk, 7.4% of the observations, had missing values.
So just holes in the data.
Exactly. And in the raw files, these weren't just left blank. They were literally marked with a question mark character.
A literal question mark. Okay. So where were these holes? Were they just scattered randomly across the data set?
They weren't. They were concentrated in 3 specific variables: occupation, work class, and native.country. Now, a novice data scientist or someone in a hurry might just say, delete them. Let's just throw away those rows. I want perfectly clean data to work with.
Sure, that makes sense. Get rid of the incomplete files. Great.
It seems logical, but it's incredibly dangerous. You have to perform what you might call data forensics. You have to investigate the mechanism of the missingness. Is the data, I'm sure, missing completely at random?
And what does that mean? It's like, did the dog just randomly eat the homework, or did the student hide the homework because the grade on it was bad?
That's a perfect analogy, exactly. If it's truly MCR, if it's random, then deleting those rows is probably fine. But Li Peng Chen and the team, they investigated this. They looked at the relationship between having a missing value and the person's actual salary.
And what did they find?
They found a very clear pattern. The people who had those missing values, the ones with the question marks, were significantly more likely to have low salaries compared to the people who had complete data.
Ah, so it's not random at all. There's a story there. Maybe people with lower incomes were less likely to want to report their occupation. Or maybe they were between jobs, which would explain the missing work class.
Precisely. The data was not missing at random. So if you just deleted those rows, you would be systematically removing low-income people from your data set. You'd be artificially inflating the average income. You would bias your model toward the high earners.
You'd be training your AI on a fantasy world where unemployment or job insecurity just doesn't exist.
A fantasy world? So the model would learn the wrong lessons.
So what's the fix then? How did they handle these question marks without just deleting the people associated with them?
They made a simple but really effective feature engineering choice. Instead of doing complex imputation, which is where you try to guess what the value should be, they just treated the question mark as a valid answer in itself.
How does that work?
They created a new categorical level called unknown. So now for the occupation variable, you have categories like sales, tech support, craft repair, and unknown.
That's really smart. It turns a lack of data into a new data point. The fact that I don't know what you do for a living becomes a feature, not a bug.
And a predictive one at that. As we saw, that unknown feature is actually correlated with lower income. So it's valuable information. Now, they also did some other cleanup on the variables themselves, mainly to handle redundancy.
Right. I noticed in the paper they tossed out the education variable entirely. That seemed really odd to me at first glance. I mean, education is almost always one of the top predictors of income. Why get rid of it?
They didn't throw out the concept of education, just one of the variables representing it. The dataset actually had 2 variables for this. Education, which was a text label like bachelor's or HS grad, and then another one called education.unpatiladina,
Education.ona.
which was a numerical scale from 1 up to 16, representing the years or level of schooling.
Ah, I see. So bachelor's in the text column might correspond to the number 13 in the numerical column, and master's might be 14.
You've got it. They contain the exact same information, just in a different format. And keeping both of them in the model introduces a problem called multicollinearity.
That's where 2 variables are moving in perfect lockstep, right? It confuses the models.
It totally confuses. They can't figure out which one is responsible for the effect. And since education.ghanem already captures the natural order of education, a master's is mathematically more than a bachelor's. It's a much better format for most algorithms.
Mm.
So the text version got the axe.
All about efficiency. I like it. So we've patched the holes with unknown. We've removed the duplicates. What's the next step in prepping the data? Did they split it up?
Standard procedure. They divided the 48,842 records into a training set and a testing set. The training set gets 70% of the data, and that's what's used to teach the models. The testing set is the remaining 30%, and it's kept in a locked vault, so to speak.
The final exam.
Exactly. You never, ever test your model on data that the student has already seen in class. That's cheating.
Okay. So before we actually run the models, the paper does some what they call exploratory data analysis, or EDA. This is basically just looking at the correlations and patterns in that 1994 snapshot. And I have to say, some of these stats really paint a vivid picture of that era.
They really do. And it's important to remember, the model doesn't care about social justice or history or context. It is a cold, calculating machine that only sees patterns in numbers.
Right. And it found some strong ones. For example, marital status. High income was heavily correlated with the category married civ spouse.
Very strongly. While on the flip side, low income was correlated with never married or divorced.
So being in a stable married household in the mid-90s was a massive indicator of higher earnings.
The paper even made a bit of a wry comment about it, noting that money can indeed ruin your marriage, because they saw that correlation between lower income and divorce rates. But statistically, yes, it points to the economic power of dual household or stable household structures in that time period.
And then there's the demographics. This is where you have to just report what the data says. High income skewed heavily white and male. Low income skewed black and female.
Which aligns perfectly with the broader sociological data of the U.S. labor market in 1994. The models are going to pick up on this. If being male correlates with high income in the training data, the model will absolutely use gender as a predictive feature. It have no choice.
And education, no big surprise here, showed that high income was tightly linked to having a bachelor's degree or higher. But here's a really crucial technical point the paper highlighted: the distribution of the numerical variables. Things like capital gain or hours per week.
This is so important for anyone listening to visualize. If you were to plot a histogram of the ages or the capital gains or the hours worked for everyone in this data set, you do not get a nice symmetrical bell curve.
It's not a bell curve. I thought everything in statistics was a bell curve.
Not in the real world. Real world data is messy. Take capital gain, for example. For 90-something% of the people, the value is 0. They have no capital gains.
Right.
And then for a tiny fraction of people, it's a huge number. The graph looks like a giant skyscraper right at 0.
Yeah.
And then a long, flat plane with a few tiny bumps way out in the distance. It is heavily skewed.
Okay, and why is that a problem?
Because it's a massive red flag.
Yeah.
Many of the classical statistical models we're about to discuss, they operate on an assumption of normality. Their internal math assumes the world looks like a bell curve. If you feed this lumpy, skewed real-world data into them without fixing it first, they tend to choke.
Okay, well then let's see them choke. Or at least, let's see how they handle the pressure. We're moving into section 2 of our deep dive. The baseline models. These are the linear approaches. And we're starting with the granddaddy of all classification, logistic regression.
Logistic regression is the absolute bread and butter of binary classification. It's elegant, it's interpretable. Instead of trying to predict the salary directly, which is a continuous number, it models the probability of the salary being high.
The probability. So it gives you a number between 0 and 1.
Exactly. And to do that, it uses something called the logit function.
Walk us through the mechanism here. How does it think? What's going on under the hood?
Okay, so it takes all of those inputs we talked about, age, education number, sex, hours per week, and it assigns a weight or a coefficient to each one. It then sums them all up in a big linear equation. Just like in high school algebra, y equals mx plus b, but with many more terms.
Okay, but a linear sum like that can give you a number that could be anything. It could be negative 500, it could be positive 1,000,000. You just said probabilities have to be between 0 and 1.
Precisely. So it needs a way to squash that result. The logit function, or the sigmoid function, is a beautiful S-shaped curve that takes any number, no matter how big or small, and squashes it into a value that is always between 0 and 1.
So it turns the raw score into a plausible probability.
That's its whole job.
Yeah.
And to find the best possible weights for that initial equation, It uses a method called maximum likelihood estimation, or MLE.
MLE. We hear that term thrown around a lot. What is it actually doing? What does it mean to maximize the likelihood?
Imagine you're trying to tune an old analog radio. You've got a lot of static, and somewhere in there is a clear signal. MLE is the process of turning that tuning knob very carefully until the likelihood of the signal you're hearing matching the true radio station is maximized.
So it's asking what setting of these weights, these coefficients, makes the data that I am actually looking at the most probable, the most likely outcome.
You've nailed it. That's exactly what it's doing. And the researchers in this paper, they didn't just build one version of this model. They tried 3 different versions to find the best possible tune.
Right. What were the contenders?
They did. Model 1 was just the intercept, basically, the dumb guess model. Useless. Model 2 used only the numerical variables. And Model 3 used all the variables available, both numerical and categorical.
And Model 3 was the winner.
Model 3 was the clear winner. They validated this using something called the AIC, the Akaike Information Criterion.
AIC is like a scorecard for models, right?
It's a scorecard that penalizes you for showing off. It rewards a model for being accurate, but it subtracts points if you use too many variables to get there. It's looking for elegance. The simplest explanation that fits the facts. Model 3 had the best balance of accuracy and simplicity.
Okay, so logistic regression is our baseline. It draws a nice simple curve and says, above this line is probably high income, below this line is probably low income. Now let's move to the next one. Linear discriminant analysis, or LDA. This feels like a totally different philosophy.
It is a completely different way of thinking. It's not just drawing a line. It's looking at the shape and distribution of the data itself.
How so?
LDA essentially flips the problem on its head using Bayes' theorem. Instead of asking, given this person's age and education, what is their probable class? It asks a different question. It asks, given the class high income, what is the likely distribution of age and education for people in that group?
So it kind of works backward from the answer.
In a way, yes. There are a few steps. Step 1, it looks at all the high earners in the training data, and it tries to model the shape of their features, assuming it's a bell curve. Step 2, it does the exact same thing for the low earners, modeling their bell curve.
So it builds 2 different profiles, one for each group.
2 statistical profiles.
Yeah.
Then in step 3, when a new person comes along, it calculates the probability of that new person's data fitting into the high-income profile and the probability of them fitting into the low-income profile. Whichever is higher is the prediction.
That actually sounds a lot smarter and more nuanced than just drawing a single line.
It is extremely powerful, but it has a fatal flaw, which we already hinted at earlier. LDA makes very, very strict assumptions about the data.
The bell curve.
The bell curve. It assumes that the predictors are all normally distributed, perfect bell curves, and, this is the other key part, that each class, high and low income, has the same variance, the same shape, and spread to their data clouds.
And we already know from the EDA that our data is definitely not a collection of pretty bell curves. Capital gain was that one giant skyscraper.
Exactly. So we have technically violated the rules of LDA before we've even started. The researchers proceeded anyway, to see how it would handle the adversity, but we should expect it to struggle.
Okay, so if LDA is the strict parent with all the rules, what if we loosen the tie a bit? That brings us to the next model, QDA, quadratic discriminant analysis.
QDA is LDA's more flexible, more relaxed sibling, where LDA assumes that the high-income group and the low-income group have the exact same shades, the same covariance matrix.
The same data cloud shape?
Right. QDA says no, let them be different. It allows for what we call heterogeneity of variance. It lets each class have its own unique shape and orientation in space.
So the high-income cloud can be wide and flat, and the low-income cloud can be tall and skinny, and the model is okay with that.
It's perfectly fine with that. And because of this flexibility, it allows for a quadratic boundary. Instead of a straight flat line separating the two groups, you can get a curved, parabolic, or even a circular boundary. It's much more adaptable.
But there has to be a cost for that flexibility.
There is. The cost is complexity. To allow for those different shapes, QDA has to estimate many, many more parameters than LDA. And looking at the paper, this is where QDA ran into a serious show-stopping wall.
Right. They encountered something called rank deficiency, and the way they had to fix it felt a bit like performing surgery with a sledgehammer.
This is a fascinating mathematical dead end that you run into with real data all the time. The model tried to compute something, and it just broke because some of the categorical variables were linearly dependent.
Hold on. Linearly dependent. I remember that term from algebra. But in the context of predicting someone's income, What does that actually look like? Why did the math break down?
Think of it like trying to solve a Sudoku puzzle where two of the rows are absolutely
You
identical.
can't solve it.
You can't find a unique solution because you have redundant information cluttering up the grid. In QDA, the algorithm needs to invert a matrix for each class, which is the mathematical equivalent of division.
And you can't divide by 0. That's the one rule everyone remembers.
That's the rule. And because some of the variables, especially native country and work class, had so many different categories, and some of those categories perfectly predicted others, the determinant of the matrix went to 0. The algorithm looked at the data and essentially said, I have infinite possible solutions here. I can't pick just one. The math just failed.
So the model just froze. It couldn't run.
It froze. It threw an error. And to make it run at all, the researchers had to forcefully remove those three variables that were causing the problem: work class, education, and native.country. Which is like telling a boxer they have to fight, but first you're going to tie one of their hands behind their back.
You might finish the fight, but you're not going to win.
You're not going to win. And this really marks the end of the linear era in our comparison. We've hit a wall. Logistic regression is maybe too simple. It can only draw a straight-ish line. And LDA and QDA are too fragile. They demand the data be shaped like a perfect bell curve, which real life never ever is. We need something that doesn't care about the shape of the data. We need a brawler.
Well, we need the support vector machine.
Yes, the SVM. This is a completely different animal.
I always visualize this one as trying to slice a cake, but the cake exists in 14 dimensions.
That's a great visualization. Imagine all your data points are floating in a giant room. Some are red dots for high income, some are blue dots for low income.
Yeah.
The SVM's job is to find a hyperplane, a flat sheet of paper or glass, that it can slide into that space to perfectly separate the red dots from the blue dots.
Okay, a dividing wall.
A dividing wall. But here's the key. It doesn't just want to separate them. It wants to find the wall that creates the widest possible margin on either side.
The margin, what's that?
The empty space. The
Yeah.
gap. It wants that sheet of glass to be as far away from the nearest red dot and the nearest blue dot as possible. It's not just a divider, it's a super wide, safe highway between the two classes.
But wait a minute, we have almost 50,000 data points. That's a very crowded room. Drawing one single straight sheet of glass through that without hitting any of the dots seems, well, impossible.
In most real-world cases, yes, it is impossible in the original dimensions. And that's where the magic of kernels comes in. A kernel is a mathematical trick that can project that messy data into an even higher dimensional space where it does become separable. It's wild.
So it adds a dimension to untangle the knot.
Exactly. However, for this specific paper, the researchers made a very practical, very real-world choice. They stuck with a linear kernel.
A linear one. Why? If the fancy curved kernels are so much better at separating the data, why would they settle for a simple linear one?
2 words: computational cost. The time complexity of training in SVM is, roughly speaking, on the order of $2
Woo! Back up there. Let's translate that for my laptop. What does that mean?
So $2 is the number of observations. We have nearly 50,000 people in this data set. If you have to square 50,000, you get 2.5 billion.
Billion.
With a B, 2.5 billion operations, just as a baseline. And if you start using a complex kernel like a radial basis function, the math gets even heavier. On the hardware available in the late 90s or even the early 2000s, training that model could take days, maybe even weeks. It just wasn't feasible.
So they kept it linear for speed, a practical trade-off. Did they just guess the settings for this linear model?
No, they tuned it carefully. They used a technique called tenfold cross-validation to find the optimal value for the cost parameter, which is usually denoted by a capital dollars.
The cost parameter. This is basically telling the model how much it should panic when it misclassifies a data point, right?
That's a perfect way to put it. If $2 is really high, the model is a perfectionist. It's strictly punished for any single point that ends up on the wrong side of that highway. This can lead to overfitting, where it creates a really squiggly boundary just to be perfect.
And if C is low?
If $2 is low, the model is more chill, it's more relaxed, it's willing to accept a few errors, a few dots on the wrong side of the road, in exchange for a much wider, safer, more generalizable margin. And for this data set, they found the sweet spot was a relatively low cost, $2 apiece, 1 and 1.
Okay, so SVM is our high-dimensional slicer. Next up, we have the random forest. This is one of my favorite concepts in machine learning just because it's so intuitive. You literally build a forest of decision trees. But my question is, why a whole forest? Why not just build one giant super smart tree?
Because a single giant super smart tree is usually a neurotic, over-caffeinated mess. If you build one huge, deep tree and let it grow unchecked, it will perfectly memorize the training data.
Memorize.
It will learn that John Smith, who is 42 years old and lives at 123 Maple Street, makes more than $50K. That's great for predicting John Smith's salary, but it's completely useless for predicting anyone else's. It overfits terribly.
So how does building a whole forest fix that problem?
It uses two brilliant tricks. The first is called bagging, which is short for bootstrap aggregation. It builds hundreds of different trees, in this case 300 of them, but each tree is built on a slightly different random sample of the original data. Some trees might see John Smith's record twice, some might not see it at all.
So each tree gets a slightly different perspective on the world.
A different curriculum. And the second trick is the real secret sauce. The trees themselves are also limited. At each split, at each decision point in the tree, the algorithm is not allowed to look at every single variable to make its choice.
It's handicapped.
It's handicapped on purpose. It's only allowed to consider a small, random subset of the variables. In this paper, they tuned that number. It's a hyperparameter called mtree, and found the magic number was 3.
Only 3 out of 14 available variables.
Yes. Think of it like trying to get advice from a committee of experts. If everyone on the committee is allowed to listen to the smartest, most charismatic person in the room, let's say that's the relationship variable in our data, then everyone is going to end up with the same opinion.
Right, they all just copy the leader, the trees become correlated.
They become clones of each other.
Well-
But by forcing one tree to only look at, say, age, hours per week, and capital loss, you force it to find new, creative, hidden patterns that the other trees might have missed. You decorrelate the trees.
It's like asking a committee for their final recommendation, but you force each member to only look at a different chapter of the evidence binder so they don't all just copy each other's homework.
That is exactly what is happening. And when you average the votes of 300 of these diverse, uncorrelated specialist trees, the individual errors cancel each other out, and the true, robust signal remains.
So how does a single tree actually make a decision? How does it know that splitting on age 30 is a better move than splitting on hours per week 40?
It uses a mathematical metric called the Gini index.
The Giannini index, I know that from economics, measuring inequality. Is it the same thing?
It's related, but here it's used to measure impurity. Imagine you have a bucket of red and blue balls.
Okay.
If all the balls in the bucket are red, the purity is perfect, the bucket is pure, and the Gini index is 0. If it's a 50-50 mix of red and blue, the bucket is maximally impure.
Okay.
The tree's goal at every step is to find a split, a question to ask that results in the purest possible buckets on the next level down. It wants to minimize the Gini index.
So 300 trees, each randomly sampling the data, each only allowed to look at 3 variables at a time, all trying to make the purest splits possible. That's our random forest.
It's the forest.
Now we arrive at the final contender, the one the paper hints is the best method, boosting.
Boosting is fascinating because it's also an ensemble of trees, just like random forest. But the philosophy behind it is completely fundamentally different. Random forest builds hundreds of independent trees in parallel. They don't talk to each other.
Right, they're independent consultants.
Exactly. Boosting, on the other hand, builds trees sequentially, one after another after another.
Okay, so one at a time.
Yes, and here's the absolute key to understanding it. Each new tree that is built cares only about the mistakes that the previous tree made. It focuses exclusively on the residuals.
Explain that. What are residuals in this context of yes, no, high, low income?
Let's use an analogy. Think of it like a game of golf. You're standing on the tee box, and your goal is to get the ball in the hole. The hole is the truth, correct prediction for a person.
Okay, I'm with you. I'm visualizing the fairway.
Your first tree, let's call him tree A, steps up and takes a big swing. He hits the ball 200 yards. It's a decent shot, but the hole is 250 yards away, so he's still 50 yards short and maybe a little bit to the right.
So his error, his residual, is that remaining 50 yards.
Exactly. That vector, 50 yards forward and a bit to the left, is the residual. Now, in a random forest, the next tree would just ignore tree A completely, tee up a brand new ball, and try to hit a hole-in-one from the start. They don't learn from each other.
But in boosting,
In boosting, the second tree, tree B, doesn't go back to the tee. He walks out to where tree A's ball landed. He looks at the residual. He doesn't try to drive the ball 250 yards. His only job is to model the error. He says, my job is to hit this ball 50 yards and a bit to the left.
so he's not predicting the outcome, he's predicting the mistake of the previous model.
He is predicting the mistake. And then the third tree comes along and corrects the tiny mistake that the second tree made on its little chip shot.
You stack thousands of these tiny incremental corrections on top of each other. You aren't building one genius brain. You're building a long chain of critics, where each one's only job is to fix the last guy's mistake.
And the paper mentions they used a shrinkage parameter for this, a lambda.
The lambda, that's the learning rate. And they set it to a very, very small number, 0.03. This means that each tree is only allowed to correct a 20 fraction of the remaining error. It's like telling each golfer they're only allowed to take a very small, gentle swing.
Why so small? Why not let them take big swings and fix the problem faster?
To prevent overcorrecting. If you swing too hard to fix the 50-yard error, you might blast the ball 100 yards and end up even farther away from the hole on the other side. By taking these tiny, timid steps, dash your 0.03 of the error at a time, you slowly, surely, methodically creep up on the perfect answer.
It takes longer, I assume.
It takes much longer. That's why they had to use 10,000 trees for the boosting model.
10,000. But here's the kicker, the detail that blew my mind. I saw in the paper that the interaction depth for these trees was set to 1.
The interaction depth, yes. For the listeners, that's just how many questions a single tree in the model is allowed to ask, how many levels deep it can be.
Right, and a depth of 1 means the tree makes exactly one decision. It asks one question. Is the person married, yes or no? That's it. That's the entire tree. We call those decision stumps.
That seems incredibly weak, doesn't it?
Hey.
A single yes-no question can't possibly predict income with any accuracy.
Exactly. On its own, a single decision stump is an idiot. It's barely better than a coin flip. But what this proves is that you can build a superintelligence out of 10,000 idiots, provided each idiot meticulously listens to the one that came before him and focuses only on fixing that one specific mistake.
That is a profound and perfect definition of what gradient boosting is doing.
So the stage is set. We have our 6 fighters, logistic regression, LDA, QDA, the SVM, random forest, and this sequential army of decision stumps in boosting. The data has been crunched. The training set has done its job. Now, the moment of truth, they unlock the testing set. What happens?
They measured the performance using a couple of key metrics, but the main one was the ROC curve. That's the receiver operating characteristic curve, and its summary statistic, the AUC, which is the area under that curve.
Okay, give us the quick refresher on AUC. What's a good score?
An AUC of 0.5 is a coin toss. It means your model has absolutely no discriminatory power. It's just guessing. An AUC of 1.0 is a perfect godlike model that never ever makes a single mistake. Anything above 0.8 is generally considered good, and above 0.9 is excellent.
And the final scoreboard.
Well, it's actually a very tight race at the top. 4 of the models performed exceptionally well. Logistic regression, the SVM, random forest, and boosting all scored an AUC greater than 0.9.
So all the more modern, complex methods did really well.
They did, but there can only be one winner on the scorecard. And the crown in this paper goes to boosting. It achieved the highest AUC of 0.9192. And importantly, it also had the highest overall prediction accuracy, correctly classifying 86.33% of the people in the test set.
86%. So it beat that no information rate of 76% by a full 10 percentage points.
Which is a massive, massive margin in data science. That 10% represents the model's true ability to actually distinguish between the classes, rather than just relying on the lazy majority class guess.
And who is at the bottom of the leaderboard? Who was the loser?
Poor QDA. It came in dead last with an accuracy of only 76.19%.
Ouch. That is barely better than the dumb guess we talked about at the beginning.
It's statistically indistinguishable, really, and it just confirms our suspicion. The forced removal of those important variables because of the Sudoku problem, that rank deficiency, combined with the fact that it was built on an assumption of normality that was just completely false, it crippled QDA. It never even stood a chance.
Now, there was a really interesting nuance here with the random forest model. The paper says it had the best F measure. What is that, and why does it matter if it wasn't the most accurate?
The F measure, or F1 score, is the harmonic mean of 2 other metrics, precision and recall. Precision asks, of all the people you predicted were high income, how many actually were? Recall asks, of all the people who truly are high income, how many did you manage to find?
So it's a balance.
It's a balance between being cautious and being aggressive. And random forest was slightly better at that delicate balance. But, and this is a huge but, its overall accuracy was significantly lower, only 76.67%, barely beating out the disastrous QDA.
Wait a minute. How is that possible? Random forest had a great AUC, over 0.9, which means it was good at ranking people, but it had a terrible accuracy score. How can both be true?
That is a fantastic catch, and it's a super important concept. AUC measures ranking. It means that generally the random forest model gave higher probability scores to the rich people than it did to the poor people. It knew who was who.
But
But maybe it was too hesitant to pull the trigger on the final prediction. For example, maybe gave a rich person a probability score of 0.49. The model knew that person was richer than someone had scored at 0.1, but because the cutoff is 0.5, the final prediction was still no or low income.
so it had the knowledge, but it lacked the conviction to make the final call.
That's a great way to phrase it. It had the ranking knowledge, but not the classification conviction. Boosting, however, was the complete package. It had the high AUC and the high accuracy.
And speaking of conviction and that .5 cutoff, the paper did something interesting there with the boosting model. Usually you just say if the probability is greater than .5, you predict high income, but they tweak that number.
They did. They optimized it. They ran a search across all possible probability thresholds from 0 to 1 to find the exact cutoff point that would maximize the final accuracy on the training data. And they found it wasn't exactly .5. They shifted the cutoff ever so slightly to .5022.
That's a tiny shift, .002. That feels like splitting hairs.
It is. But in a data set of nearly 50,000 records, shifting that goalpost just that tiny little bit can reclassify dozens or hundreds of people correctly. It's the final turn of the screw to optimize the confusion matrix and squeeze out that final fraction of a percentage point of performance, getting them to that final 86.34% accuracy.
Okay, so we know boosting won, but I want to talk about the why. What was the winning model actually looking at? The paper lists the relative influence or variable importance for the boosting model. This is the moment we find out what actually predicts wealth in America, at least according to this 1994 data set.
This is the narrative payoff. The algorithm itself can tell us what features it found most useful for making its decisions. The boosting algorithm identified the top 3 drivers of income. Coming in at number 3 was capital gain.
No surprise there. If you have significant investment income, you're very likely to be in the higher income bracket.
Makes perfect sense. Coming in at number 2 was native country. So a person's geographic origin played a very significant role in the model's predictions.
And number 1, the single most influential factor that this ultra-complex 10,000 tree model decided was most important.
Relationship.
Relationship, not education, not occupation, not the number of hours you work a week.
No. Relationship, which is the variable that includes categories like husband, wife, unmarried, own child, was the single most dominant predictor in the model. It had more relative influence than anything else. It outweighed education and occupation in the final structure of the boosting model.
That is absolutely mind-blowing. I mean, we saw the simple correlation in the EDA at the beginning, but for the most advanced algorithm to confirm and say that this factor is more important than the actual job you do or your level of schooling, that's incredible.
It really speaks to the powerful correlation between household structure and economic stability in this particular data set. To make this less abstract and more concrete, the researchers did one final thing. They fitted a simple, single decision tree, not for prediction, but just to visualize these logic paths for us.
Okay, walk us through those paths. If I am a person in this data set, how does this simple tree sort me into a high or low income bucket?
Okay, path 1 is the clearest. The first question the tree asks is, are you highly educated? Is your education number greater than or equal to 12, which is basically a bachelor's degree?
Yeah.
If the answer is yes, it asks a second question. Are you married? Specifically categorized as husband or wife. If the answer to that is also yes, the tree almost immediately sorts you into the high-income bucket. End of story.
So in this data, education plus marriage was a very strong signal for success.
A very strong signal. Now, path 2. What if you are married, but you are less educated? In this case, the tree says your income depends almost entirely on your capital gain. If you have significant capital gains, you're sorted into high income. If you don't, you're sorted into low.
And the third path, what about the unmarried people?
Path 3 captures everyone who is unmarried. This includes the categories own child, other relative, unmarried, and so on. For this entire group, the tree finds that income is almost entirely determined by one factor, capital gain. Without the marriage factor in the equation and without high capital gains from investments, the model overwhelmingly predicts low income.
Wow. So according to this simple model's logic, Being single and working a regular job wasn't really enough to trigger a high income prediction unless you also had significant investment gains on the side. That is a really stark picture of the 1990s economy.
It is, and it shows exactly why boosting won. It was able to capture these complex, non-linear interactions, the way that marriage seems to amplify the effect of education, or the way capital gain acts as a sort of safety net for the less educated married folks. A simple linear model just adds these effects together. Marriage plus education. Boosting is smart enough to understand that it's more like marriage times education.
So let's wrap this up. What's the final takeaway here? We set out on this deep dive to find the best algorithm for this salary prediction challenge.
Well, the technical winner is indisputably boosting. For this kind of messy tabular data with lots of categorical variables, a lot of skewness and complex social interactions, it just handled the complexity better than everything else. It really proves that for this type of problem, these sequential ensemble methods are king.
And the broader statistical takeaway.
Don't ignore your assumptions. LDA and QDA failed spectacularly because the data fundamentally broke their most basic rules. You cannot force messy, non-normal, real-world data into a model that assumes the world is perfect and normal and expect to get miracles.
The researchers did note some limitations in their own work, didn't they? They pointed out ways this could be even better.
They did, which is the mark of good research. They admitted that some of the categorical variables, like native country, had way too many levels, what we call high dimensionality. They suggested that grouping some of those countries or jobs together into broader categories might have simplified the problem and helped the models even more. And they suggested in the future, more modern techniques like neural networks or XGBoost, which is an even more advanced and optimized version of boosting, could probably push that 86% accuracy even higher.
They also mentioned looking at how the predictors relate to each other, not just to the final salary, using something called graphical models.
Right, which is a whole other level of analysis. Instead of just asking, does X cause Y, you're asking, how does education influence your choice of occupation, which then influences your marital status, which then altogether influences your income? You're modeling the entire web of dependence.
That sounds like a topic for a whole other deep dive.
Oh, absolutely.
I want to leave our listener with this one final thought as they're driving. We saw very clearly that the algorithm identified relationship as the #1 predictor of wealth in this data. The machine found that pattern cold, but the algorithm has no idea why that pattern exists.
Correlation is not causality. It never is.
Exactly. Does being married cause you to earn more money? Maybe the stability of a dual income household allows you to take more career risk and get better jobs, or is it the other way around? Does earning more money make you a more attractive partner, thus making you more likely to get married in the first place? Or was the 1990s corporate and social world in America simply structured to favor and promote married men with families?
The data shows us the powerful link, but the arrow of causality, the direction of that relationship. That's a story the numbers alone can never tell us. That requires history, sociology, and human interpretation.
And that is where we leave it. The machine can predict the salary with 86% accuracy, but it takes a human to understand the life behind the number. Thanks for diving deep with us today.
It was a pleasure. Keep questioning the data.
We'll catch you on the next one.